Hello all. This is Vasu Sham, and I am joined today by Nikhil Kalyanapuram. Hello, Nikhil.
Hi, thanks for having me on.
Yeah, my pleasure. So Nikhil is now a PhD student at Penn State, working with Jacob Borgelli. And we are going to discuss Weinberg's soft theorems and their celestial holographic manifestation. Is that fair to say, Nikhil?
Yeah, I think that's fair to say.
So that's the focus, or has been one of the points of focus of Nikhil's research during his PhD. Would you like to say a little bit about your more general interests before we zoom in on the specifics?
Yeah, so my general area of interest is scattering amplitudes in quantum field theory, which generally in quantum field theory courses, scattering amplitudes are just objects we calculate to compute what the probability is for, say, a certain number of particles to scatter off of each other and produce other particles or decay or even get absorbed. But it turns out that scattering amplitudes are severely constrained by features of quantum field theory that we know are true, like the fact that all probabilities add up to one, which at the level of amplitudes translates into some feature of them as complex functions. They're also constrained by physical symmetries, like Lorentz invariance and gauge invariance and so on. So the question really is, if you have a set of data like this, that you know, for example, that a scattering amplitude has to obey unitarity, it has to transform correctly under certain symmetries, how much information can you get about the scattering amplitude without actually having recourse to quantum field theory? So that's the broad question that's sort of the broad area I've been working on. Now, it turns out there are lots of interesting subdivisions of this field where you can really go deep into the mathematics. And that's what I've been doing over the last 1 year. Or you could focus on lower level questions, like specific issues of infrared divergences, like I used to work on. There are several areas like this, but the broad area is scattering amplitudes.
Thanks, Nikhil. So the part you mentioned about what you worked on before is going to be the focus of what we're going to discuss today, which are the infrared issues in quantum field theory. Yeah. And oddly, it seems like if we took a historical look at the development of the subject, in the previous century, most of the focus was on understanding how to handle the ultraviolet divergences and sort of like understanding sensitivity to ultraviolet behaviors of amplitudes. And there it made sense to be very concerned with the very specific forms of the theories that people were trying to put together, because it wasn't entirely understood to what extent you can get away without doing so. But in more recent years, with I don't even know exactly where to plant the flag and say that this was when the perspective shifted. I guess the focus has shifted more towards understanding infrared aspects of scattering amplitudes, in part with the hope of connecting ideas of the amplitude world to the ideas of the gauge gravity duality and holography and so forth, which will also be a sort of focal point of what we're discussing today. So, I mean, does that ring true to you, this impression?
So it's a good summary of the broad historical approach to these subjects, because the reason why one of the problems with scattering amplitudes as mathematical objects is that they're not finite in any strict sense. They contain divergences almost everywhere you calculate them, and that's meant as an exact statement because they really are functions of the variables that they take in, which tend to be the energies of the particles that are scattering, the masses of the particles, and so on. Most of the time, for most values of energy that we're really interested in, as far as collider physics are concerned, or even to various orders of approximation that we want to study, scattering amplitudes tend to be infinite. Now, historically, the divergence problems that showed up in scattering amplitudes, the ones that really bothered people were the ones that were infinite when you went to very large values of the momentum, because it seemed to signal that there was something fundamentally wrong with the theory. The idea that you can't make the particles arbitrarily fast, which is what happens when you make them more and more energetic, Of course, capped by the speed of light, but with that caveat, make them arbitrarily fast. The fact that scattering amplitudes in these limits were not finite really bothered people because this was an obstruction to actually carrying out calculations to higher and higher orders of precision. Because calculations of amplitudes for very large momenta, that's really where they occurred, when you had to calculate answers to higher precision. And of course, we now know that this problem was resolved was resolved in the form that we recognize today by Schwinger, Feynman, and Tomonaga in the late 40s, when they realized that these infinities are in some sense not real, that so long as you're always doing your calculations consistently, you can reabsorb these infinities into various values of the coupling constants. That later evolved into a more complex story about renormalization, about which you know much more than I do. But uh, it was nice to see that at least the ultraviolet divergences could be controlled in some way. And as Weinberg himself mentioned, this turned out to be a very beautiful way of actually classifying quantum field theories, or it was thought at the time, because theories that could be controlled this way were special in a way that theories that could not be controlled were not. But the other class of divergences were IR divergences, which occur when one or more particles have very low energy, where they, calling them slow is perhaps not the right way of saying it, but where looked at as waves, the particles have extremely long wavelengths. And these divergences for a while were regarded as entirely spurious, because the occurrence of divergences were viewed as some constraint on the extent to which you could actually measure wavelengths. So people thought, okay, a measuring apparatus can't control for wavelengths that are longer than a specified length, because we have precision problems. And so long as you adjust for those precision problems, you cut off the wavelength at some large scale, everything is fine. So this is how infrared divergences were handled for most of the 20th century, because people thought that so long as you cut off your wavelengths appropriately, you're fine. And they actually produced physically meaningful results, which you could then test in labs, and they all matched perfectly well. But I think where the resurgence of this interest comes from was to realize that long wavelengths actually mean something in quantum field theory, which is something that we've been overlooking for a while, which is that they only occur in theories that have massless particles. And what long wavelengths mean in terms of space-time mechanics is stuff that occurs in some precise sense of infinity. So you have all these particles scattering off inside the bulk in four-dimensional space-time. And if you go to the boundary of space-time and go to very long distances, the only interactions that really survive are the ones that are mediated by massless particles. And the only ones that are actually captured by infinity are the ones that come from those particles which are wavelengths long enough to actually reach infinity. So once I think it was realized that you could understand a lot about quantum field theory at the boundary by studying infrared divergences in the bulk, that's when I think the interest in this, in what is very loosely referred to as a duality, showed up. And that's when the resurgence of this interest in IR divergences came up. And it turns out there's a lot of wonderful literature in gravitational physics that actually ties into all of this stuff that people had already been thinking about in the 70s, but in the context of GR, not in quantum field theory. So I think much of the modern work has really been developing a dictionary between these two things.
Right. Well, that was a very good layup, or I guess a setup for what we will now discuss, which are some of Weinberg's original papers on the topic of infrared divergences, written at a time where perhaps these weren't on top of everybody's list of concerns. And
yes, he makes that clear in the introduction, as we'll see.
Yeah, but you see, what you mentioned with quantum electrodynamics being the paradigmatic example of a situation where the ultraviolet divergences had a recipe for being controlled is something that he also comments on. So let's take a look. So we'll begin with the background, and there's no better background than Weinberg's original papers. And what we intend to do is have this discussion snowball into Nikhil's subsequent work and works related to some of his papers that we're discussing. But I'll be achronologically going through some of Weinberg's papers, and I thought the first one to talk about, since we talked about infrared divergences, is the following one from 65, titled Infrared Photons and Gravitons. And you see here that he makes it a point to say, well, you have infrared divergences that arise in quantum theory involving the gravitational force or quantum electrodynamics, but that they can actually be removed using familiar methods used in quantum electrodynamics, right? So he makes it a point to say that, well, insofar as you're concerned with how they infect physical observables such as rates, we'll show you how to deal with them using regular methods in quantum electrodynamics, and we'll make that more precise. And then he also talks about how, there are two kinds of these divergences, and they come from either emitting very low energy photons and gravitons off of the external legs of some other process, or you have them running between the external legs of some other process while still maintaining the on-shell nature of the momenta running in these lines. So basically, I mean, I won't go through the abstract. This is just one sentence that I'll try and read out. But the basic picture of, like all the mechanics that will follow starts with the following process, right? So you think about some arbitrary process denoted gamma here. So I've borrowed this from Ashok Sen's paper from 2017. Yes. Here he was looking at...
I think he's one of the few people who uses gamma as a symbol for scattering amplitudes.
Yeah, it's a kind of old-fashioned way of thinking. But his concern, and this is actually an interesting point to bring up, because we were discussing the salience of like ultraviolet divergences in comparison to infrared and so on. And what happens in string theory is that there's a sort of resolution of the ultraviolet issue beyond what you have in renormalized quantum field theory. It's fair to say that it's a mechanism beyond what you have in renormalized quantum field theory. Now, what you're left with there is going to still be the infrared issues. And so Sen, being sort of aficionado of string field theory and, trying to hammer at some of the more fundamental, deeper questions in string perturbation theory, thought it important to understand how to resolve the issue of infrared divergences, which also affect these ultraviolet finite string amplitudes. So yes. that was part of his motivation in this paper. I mean, this paper mostly has to do with string field theory and IR divergences, but he started with a field theoretic warm-up where he considered one external leg of this process to which is attached a soft graviton line. This could very well be a soft photon line. And the idea here is to basically consider the net contribution of this line in the limit where k is small, and when we take this external line to go on shell. Right. So just from our understanding of basic quantum field theory, we see that the data that this involves will be a vertex, and it will be the propagator of this line, right? So let's start with the case of attaching one soft photon, and let's take, for simplicity, this process to be involving just scalar particles, some charged scalar particles. Then, well, you're going to have vertex, which is momentum dependent, because you've just taken the kinetic term, you've covariantized it, and that'll give you a vertex. And then there's going to be the propagator, which has now injected into the momentum factor an extra factor of Q, which is what Sen denotes K here. And eta here is the sign that tells you whether this is an incoming or outgoing line.
Right.
So this is all a little bit dependent on the specific form of the vertex for charged scalar interacting with the photons, scalar QED. But in the limit that we described, where Q goes to 0 and the P squared equals minus M squared, that is that the external line goes on shell, we recover a universal factor here for the photon case. So it's basically 1 power of the momentum multiplied by the charge divided by P dot Q shifted by I epsilon.
Right. If I could just make one comment here.
Sure.
The universality of this is easily checked. You can say take a fermion and a spin half particle and attach a soft photon or a soft graviton to it and see that you get a factor like this.
Right.
But the other way of seeing it is in some sense that the factor really couldn't have been anything else at leading order.
Mm-hmm.
It's really fixed by Lorentz invariance in a very strong way, because you see the external photon is the wave function of the external photon is just a polarization vector, which we tend to denote as epsilon, and that polarization vector has to dot against something. Now, all the other polarization vectors or all the other spinors have dotted against the amplitude, denoted here by gamma. So the only thing that the polarization vector could be dotted against is the soft factor. And the only Lorentz invariant thing that you have is either Q or P. And to leading order, you know for a fact that any linear combination of P and Q would inevitably result in P dominating over Q, because Q is so small. Now, in terms of the denominator factor, that's fixed entirely by unitarity, because that's the only Lorentz invariant piece that you can construct out of P and Q, knowing for a fact that P is on shell, even though P plus K is really only very close to on shell. Now, P dot Q as a result is the only Lorentz invariant piece that could exist, because the only other Lorentz invariant objects are Q square, which is 0, and P square minus M square, which is 0. Or in this case, in this sign convention, P square plus M square. So the soft factor at leading order is fixed entirely by unitarity. And that actually goes a long way towards really realizing the universality of all of this. In a way, the ultraviolet divergences are not universal. They depend. They really depend on the theory you're using. But IR divergences are just. This is the same in any theory. The arguments I just used do not make use of the fact that the external particles are anything.
Right. Well, that's a very good point. And in fact, as you mentioned, you could just choose this vertex to be what you like, or whatever you like, and then you'll find effectively that it's got to be the same thing by using arguments from Lorentz invariance and unitarity. And as you said, here the wave function for the external photon line is going to be 1 power of the polarization vector. In the graviton case, it would be 2. And that's why you're going to have 2 factors of momentum appearing. And again, this comes from looking at linearized gravity coupled to a scalar field. But again, in the limits that we're describing, the leading soft limit, you get a universal soft factor here too, now involving 2 powers of the momentum in the numerator instead of 1. And instead, in place of the electric charge, you're going to have the square root of 8 pi g. So those 2 things are the only modifications. And the nice thing about this paper is Weinberg just goes on to do a bunch of calculations where this is all you really needed.
Yes.
Which is very nice. So, okay, then there's, of course, the extension to say you had multiple soft photons. What's going to happen? Well, you're going to have a product of factors of this form after doing a little bit of arithmetic to convince yourself that in the leading soft limit, the effect of having these sums is somewhat irrelevant. So first thing Weinberg looks at are virtual infrared divergences. And I guess this is a nice echo of what will come in your work, where the first things you tried to go after in the 2-dimensional models, holographic models, you looked at were the virtual.
What happens to the virtual pieces? Yes. Yeah,
the virtual pieces. So here, the idea is you're taking external lines, gluing them together with some infrared photon. So the name of the game is make sure that the external lines can stay on shell.
Can stay on shell. Yes.
Yeah, you want them to be
as close to on shell as possible.
Exactly.
Yes.
Exactly.
Yes.
And so have Q be small enough, right? And so the soft limit lets you do that. And furthermore, what's nice is that knowing the soft factors and knowing the form of the photon propagator and the graviton propagator, at least in some gauge, although I don't think the gauge really matters, is that you can essentially write down the effect of having an arbitrary number of these kinds of virtual IR photon links between the external legs. Now, say you had n of them, then the result is going to be the following factor. So you're going to have the nth power of the integral between an IR cutoff little lambda to the UV cutoff big lambda of some momentum integral of A of Q, right? And this is because you have, well, virtual lines and you're just following the Feynman rules. And here, A of Q is just going to be the propagator connecting two vertices where you're going to have a soft factor each. So you're going to have a product of those soft factors, right? So this is just, let's look at this a little bit in a little bit more detail. It's just charge, eta the sign, P divided by P dot Q shifted by epsilon. And the same thing with P reverse sign, just dot it together. And so that and you just sum over all n and m, so all endpoints. And now what you do is just sum over all possible n. Notice that this is just one term in the Taylor series of the exponential function. And that's the result of having an arbitrary number of infrared virtual photon lines connecting external lines in some arbitrary process. So S naught is the S matrix without virtual IR photons. And needless to say, the story for infrared gravitons is not that different, except now your factor knows about the graviton propagator.
But the graviton propagator instead of the photon one. Yes.
Exactly. And also the fact that you have two powers of momentum in the soft factor instead of one.
Right, instead of one.
So you're going to have something quartic in the numerator here, in the momenta, where you either have contractions between different momenta, or you have contractions of the momenta with themselves, which will give you, when they go on shell, m squared. So it's the same rough format, just the difference in the details of the propagator and the details of the soft factor's numerator, right? Not even the denominator. The denominator is the same. Then what you want to consider in addition to this are the real infrared divergences, which takes us back to the point that you made about incorporating the actual wave functions of the soft photons and gravitons involved.
Yes.
So now we're no longer looking at these photons or gravitons connecting external lines, but we're just looking at these photons or gravitons just being emitted, right? So they're just sort of like flying off. And so what you need to do is just incorporate the actual wave functions of these particles. In the photon case, as you mentioned, it's going to be the polarization vector. And the polarization vector dots into the soft factor, exactly as you mentioned.
Yes.
And so for n lines, this is going to be your contribution. Now, same story with the graviton, except you have two powers of the polarization vector in the graviton wave function. And that's going to dot into the two powers of the momentum, giving you a square of what you had here. Right? So very similar format.
Very similar format, yes.
And so these are both going to lead to issues in and of themselves, right? So these contributions, the virtual contributions and the real contributions, will give you divergence as you take the infrared cutoff little lambda to 0. So to see that, we look at rates, right? So we take the modulus squared of the amplitude, and that's going to compute the rate for the process to go from alpha to beta. Now, in the virtual case, this is a rather simple story. You're going to be taking the real part in the exponent coming from taking the modulus squared. What is the real part really going to hit, right? Because A was basically propagator multiplying sums of soft factors corresponding to where the propagator connects the two external lines. Now, the propagator, when you take the real part, is going to go from this rational function of q squared to the delta function, the Dirac delta function, because basically the massless propagator is just like, well, it's not just a massless propagator. The propagator, free field propagator is essentially like the part of the principal value definition of the delta function, right? It's like one part. And then you take the complex conjugate, add them together, then what you're going to get is going to be the delta function. Right? So in the massless case, it's going to be delta function purely of q squared. And then in the real case, you're going to have, the massive case, you're going to have q squared plus m squared. And in fact, do you know off the top of your head, Nikhil, which propagator this is? So it's not the Feynman propagator, that is a time ordered one. This is probably like, is this the causal one, or?
You mean just delta q square?
Yeah, like delta Q squared or delta Q squared plus M squared.
Right. So this is, I believe, one of the causal propagators.
Right, it's the average
Because
sum over the.
right, because it's a causal propagator for obvious reasons, because it's completely onshore.
Right,
And the other causal propagator is, of course, the principal part.
right.
And
Yeah,
these of course add up in various ways to give you a causal propagators.
right. Yeah, well, that takes us a bit far afield, but these would feature in Epstein and Glasser's version
Right.
of renormalization. But anyway, here, the fact that this is a delta function makes the evaluation of this integral somewhat simple. And the result is that you're going to have a logarithm of the ratio of the UV to IR cutoffs multiplied by a dimensionless constant A. The dimensionless constant A is just the angular integral over A evaluated on Q.
Yes.
And after some algebra, you discover that it's the following function of the relative velocities between particles n and m in whosever rest frame you like.
It's perhaps worth pointing out that when he says the integral is elementary, he means in a technical sense.
Yeah,
it doesn't involve special functions. It's still a slightly difficult integral to evaluate.
Yeah, you certainly need to do a whole homework exercise on it if you wanted to.
Yes.
If you wanted to compute it, this would just be like half the homework. But fortunately, it only involves logarithm and nothing more. Now, the net contribution is coming from exponentiating this factor, which will take A to the power of this ratio. This ratio to the power of A. Yes. Yeah, the other way around. Now, of course, if you take lambda to 0, there's going to be an issue here. So now what we want to do is also look at the real soft photon contribution. So what is going to be the contribution to the actual rate, right? And so here the contribution is going to be this multiplicative factor of the product of these calligraphic A factors. And these calligraphic A factors now involve the modulus squared. So what's going to happen is that we're going to encounter a sum over polarizations of the products of the polarization vectors. So the sum over helicities of the product of the polarization vectors, right? And this object simplifies to the metric plus this symmetrized product over Q and lambda, where lambda is the following normalized vector. And because these contain explicit powers of Q and we have gauge invariance of the amplitude, the only term that matters is the one coming from G. Yes. Now, this intermediate step is something that we're going to make a big deal out of in what follows. Right. So I'll just plant a flag there. But in the end, A of Q comes out to just be something that almost looks like the contribution we had before. Right. We have Pn.Pm, and then we have two soft factors here. And again, we can witness our A of Q hat that we did the integral over before, divided by modulus Q cubed here. Right, that's what this curly A of Q is. And then Weinberg says, well, quantitatively, what you want to be doing is looking at the transition rate accompanied by any number of soft photon emissions with energy under some threshold energy. Threshold energy sets the it sets the bar for when you can consider these to be soft, right? When you can still keep the external legs on shell, and when you can consider these to be soft. But then there is
just to elaborate a bit there. Historically, E was just that number below which you could not detect photons anymore. Mm-hmm. So at any given point, you didn't know if there were photons that were being emitted which had energy less than E because the detector just didn't pick them up. Mm-hmm. Right. So when you were computing cross sections for actual measurements, which people used to do which theorists used to do in those days, theorists like us used to do in those days. You had the problem of actually making cross sections that were realizable. Right. And these had to take into consideration the fact that you probably do have a lot of soft photons which are being radiated that you're just not picking up. And to match the data, you had to include those effects because the data only really picked up the cross section in addition to these soft photons.
Right, right. So this
But your
is
theory
like
is more precise than that. And so you have to sort of adjust for the imprecision involved. And that's what most of these calculations were trying to do.
indeed. So this is basically like a sensitivity scale of some kind, this E
Yes.
of your
Yes.
detectors. So it really is morally what you would call mu in traditional renormalization theory. It's the floating
Right.
point scale. And that's how it should be seen. And we'll see exactly why that is. And you know, Weinberg's original comment about how you can deal with these divergences in much the same way as you dealt with ultraviolet divergences in QED will become clear once we keep that in mind about what big E here is. And of course, there's this IR scale lambda, which is just arbitrarily small. You really want to be taking it to 0 at some point.
Yes.
So, and then he softens the step function through this representation and computes these integrals to find the following result. So B is some known function, and you have the ratio E over lambda to the power A. Right, so this is an actual divergence. So before you had lambda over big lambda, and here you have E over lambda, still raised to the power of the same A, and you have the rate involving no soft photon emissions. And as we did before, there's just the same kind of calculation you would do for the gravitons. Now, what happens is that you have the more intricate factors here. You have the more intricate momentum dependencies, which means you're going to get a more intricate. So you just get some multiplicative factor in front of the logarithm in the virtual case, but the overall behavior is the same. You have a different
this was the point Weinberg was trying to make, that even if some of the details look more involved for gravity, the essential there is no essential difference between gravity and QED. You can use all the tech, which was a serious thing to say in those days.
Right.
That you can use QED, which was the quantum field theory back then. That you can use all the methods of QED to do things about, to do calculations in gravity, which was regarded as very difficult in those days, and it is today.
Sure. No, and it's very fascinating, and we will go over some differences in the following discussion, because when we talk about collinear singularities, there's a difference, and it might be something interesting to say about all of that. So anyway, what we have here is essentially the same kind of issue. If you wanted to take lambda to 0, it's just a different exponent. And the real contributions, again, same story. Instead of having the pi mu nu tensor, we have the tensor with 4 indices involving 4 polarization vectors. But ultimately, that breaks up into products of the 2 index objects, which then you use another argument involving gauge invariance, which, again, we are going to purposefully jump over right now to come back to later.
Yes.
To simplify the expression, now to, again, a factor that's very similar to what we had in the
virtual case.
Virtual case, exactly. And so we have the same B appearing, right? The same thing that we had before. And so you trudge through the calculations and obtain a result which looks exactly like the case with the soft photons, except we have a different exponent, but it's the same exponent as we had in the virtual case. So that's the most important story. So let's just tabulate the results. You have photons and gravitons, right? So they're their virtual and real contributions, and they all have the following effect, which is to multiplicatively change what the rates are. But they're multiplying them by a contribution, which is a ratio of scales, where one of them is the IR cutoff scale, which we ultimately want to take to 0. The statement of IR divergence is just the fact that there is a sensitivity of gamma to these scales, to this scale, which, if you just looked at the real or just the virtual contributions, will lead to a divergence, right, if you took it to 0. Now, what if you combine them? Well, if you combine them, the dependence on little lambda just vanishes.
Right. And you can take the limit to 0 because it's not there anymore.
Exactly. So it could be whatever you want it to be in principle. And that is basically the statement that Weinberg made. So the fact that you have an end result that depends only on a multiplicative factor multiplying your rate, which involves a ratio of, or in other words, which involves the floating point scale, the RG scale, the scale at which you're making measurements, the scale of your resolution of the measuring device, measured in units of the cutoff, right? Which is sort of like the important thing. that is the ultimate meaning of the statement that you can
Yes.
deal with infrared divergences in exactly the same way as you dealt with the ultraviolet divergences in QED. So that I think is an important thing to highlight, because you can then say, well, if I was using this rate as a proxy to give an effective meaning to a coupling constant, then what will happen to it, right? And so you can basically infer the contribution coming from these IR effects in principle.
And it's
So
perhaps worth mentioning that when Weinberg is saying that you can do this using the methods of QED, it was a very surprising statement at the time, because the infrared story in QED was a very old one, even when this paper was written. Because the definitive computations in terms of collider calculations were done by Feynman and Schwinger in the late 40s.
Right.
But the original calculations, I think, went back even to the 30s, if I'm not mistaken, when it was realized that, yes, you have these divergences that are annoying, but since we don't take them particularly seriously and we believe that they're coming from these deficiencies in our detectors, we have this smart way of dealing with them in QED. And QED was thought of to be this extremely special theory, which makes such perfect, and it does make such perfect predictions for all the things we want to measure. And the idea that these methods work almost verbatim for gravity was very surprising. And I think that's really the message that Weinberg is trying to get through in this paper.
Right. No, and I think that's an important point to make, and to say that we haven't fully understood the implications of that is both true and important, actually, so for what will follow. Especially when we talk about this in the context of the holographic duality, the fact that you have some particular format of scale sensitivity, which goes in the direction of having issues when you go to large distances or low energies, that is exactly what you want to map to the ultraviolet divergences, that is the divergences when you go to very high energies in the dual theory, right? If you want there to be the same notion of scale radius duality as you have in ADS-CFT. There are some very general reasons why you expect that ought to be true, coming from, like just these string constructions, for example, and so on. And if you wanted to have all this work in flat space, you probably want some version of that to be true, right? So, so that that I think is one of these key issues that we'll come back to, and we'll try to understand to what extent Nikhil has partially answered that question. So that is basically our set of basic results for the IR divergences and how they cancel. And what we'll look at next is actually a paper that came out a year before, right, which is the physical consequences of the soft emissions. And here we can be relatively quick, but we can appreciate some of these facts a little bit more. And the fact that we haven't really appreciated is that so far we have obtained these results where the rates have a factorized form when we go to the soft limit. But that came from the fact that the amplitudes also have a factorized form when we go to the soft limit, right? And in particular, if we just look at the real emissions, then basically in the soft limit, the amplitudes factor into a soft factor times what we call hard factor, for lack of a better word. Now, of course, there's a more intricate factorization we will go into, but at the very least, you have this leading order factorization, right? And so the implication of that is that as you take the soft limit, you're going to see that the amplitudes factorize, and he hasn't written it in a purely factorized form. You have to look between 4.6 and 4.8, 4.7 and 4.9 to appreciate this fact, right? So you have S here involving no soft photons times a factor that does involve the soft photons and their polarization, right? So the wave function. Same thing with the soft gravitons. And now, the fact that these are soft photons or soft gravitons doesn't negate the fact that those are gauge theories, right? Or theories that have gauge invariances, both gravity and QED. In particular, at the level of amplitudes, that implies that you have a ward identity where nobody picks up a charge. So Yeah, the sort of conventional word identities you have in theories with only global symmetries is that the result of contracting momentum into the amplitude is going to give you a sum over some local contributions measuring the charge of various objects. Here, the result is just zero. Right? The statement of gauge invariance can be equated to the fact that you have a charge operator under which nobody's charged. Right? It's another way to think about the constraints.
Right. Or alternatively, the particle that's being radiated, the external photon or graviton, is longitudinal and it's not a real particle. It's a fake particle of sorts, which means the amplitude has to be zero when something like that is radiated.
Right. And so in equations, that statement is that Q dotted with M mu for the soft photon case is zero, which this Q only hits the soft factor.
Yes.
Soft factor is P divided by P dot Q with eta E as a coefficient. And so we'll have, when you dot Q, P dot Q divided by P dot Q.
Yes.
So you get 1, leaving you only with this sum. Now, S is not 0, but the result has to be 0, meaning that this coefficient has to vanish. And so the transition must conserve charge, must conserve the signed sum over all charges. Right? So charge conservation is essentially a consequence of the soft factorization, which is very cool. But now let's go to the gravitational case where you can say something more dramatic. At least from my perspective, it was much more dramatic to see. Right? And there, play the same game. Dot Q into M mu nu, that has to vanish. Now the soft factor involves 2 powers of P in the numerator, but only 1 in the denominator. So you do P dot Q in the numerator, cancels P dot Q in the denominator, but you're left with 1P. Now, generically, all you know about momenta is that they're conserved, right? Which is a statement that the signed sum of all the momenta has to vanish.
Right.
The extra object in this calculation here is F sub n, which is the coupling of the gravitational field to the different kinds of particle species. Now, the fact that you can only have momentum conservation and not the conservation of this additional conservation, right? So that they'll contradict each other at some point.
Yeah.
But what we know as a fact is momentum conservation. So that must mean that all F sub n for any n is 1, right?
Right.
Meaning that all particles have the same gravitational charge, which is universal gravitational coupling. It's the effective meaning of universal gravitational coupling. And then Weinberg takes some non-relativistic limits to relate this fact to what you would think of as inertial and gravitational mass.
Right.
To show that the fact that for all n, F sub n is 1 means that inertial and gravitational mass have to be equal, which is another statement of the equivalence principle.
Right.
And I found this very impressive because the way in which general relativity was developed originally started with the equivalence principle. And in hindsight, when you go and try to model it, you end up with some results that kind of make you feel like you went in a big circle. For instance, if you say that the physics in any local inertial frame has to be equivalent, you say, well, doesn't that just mean that you live on some pseudo-Riemannian manifold?
Right.
Can't really tell the difference. Okay, yeah, okay, fine. And then you say, well, the statement about inertial and gravitational masses being equal, you can set up some funny model involving test particles and then playing with them. But somehow I find this to be a much more effective way to get at the heart of this fact, and it didn't even require the equivalence principle to be put in at the very get-go. And my hope for this, and this is something... sorry, go on, please.
Just a comment there. And it may or may not be something that Weinberg has emphasized, but it's worth noting that this argument must be true for any spin 2 massless particle. The idea that this is gravity is very post hoc. There was no reason for you to choose your coupling constant to even be remotely related to Newton's constant.
Right.
The only input that has gone into this, as far as Weinberg or as far as anyone is concerned, is that there's one particle of spin 2, a massless particle of spin 2, and that's interacting with all the particles in your theory. When that happens, there really is no theory that describes such a particle which is not general relativity. GR is in many ways forced on you. As long as you have one particle, spin 2 massless particle, you necessarily have to have it behave exactly like GR.
Right, right. And in fact, subtle extension of this idea became what's called the Weinberg-Witten theorem, where they then argued about
Right.
if you had some composite, right, could you
Right.
possibly have one that does what you need to? And you realize that, well, for it to be consistent with this version of the equivalence principle, the answer is, well, no. And so,
you see that a massless particle of spin 2 necessarily interacts with all the particles, because there is no other way to conserve momentum other than to have them interact with every single particle in the exact same way.
that's a very good point. That's a very good point. Yeah. And now, I mean, the obvious, at least for me, the obvious jumping off point from here is that this should then tell us that whatever theory of quantum gravity we like, or whatever we mean by quantum gravity, should then tell us what happens to this equivalence principle. Like, how do you get beyond it?
Right.
Right. Like, what is the sense in which you go beyond it? And it's a kind of weird question to pose, but I think it's a concrete one. Like, if you really wanted to say that we know what's quantum gravity, then at the very least we should say, then what became of the equivalence principle, right? And I haven't seen nearly enough papers that try to address this question. And it's not to say that it's easy, because you see, everything here is set up somehow in the IR. And you should just expect that, well, in the IR, you don't know, right? I mean, how can you tell apart different theories of gravity? In the IR, higher curvature effects are suppressed in powers of the Planck mass, so you can't ask this kind of question of that theory. But if you have a hypothesis involving a dual theory to gravity, right, some kind of gauge gravity duality, then there's a way of maybe trying to do a recasting that'll tell you something. So there, there's something special also about the low energy gravitational physics. It corresponds to actually some very strongly coupled physics of the dual theory. Right? So we will come back to that point. This will be a point of discussion in what will follow. So just to set it up, what we have seen here are the manifestations of softer infrared divergences, right? How they cancel between each other in physical processes, and the fact that the S matrix has some notion of factorization as you take the soft limits.
Right.
So now what we can do is jump to Nikhil's work, where you basically have a different perspective on it, and show that these universal soft theorems tell you that you're just compelled to look at certain two-dimensional models living on the celestial sphere, which capture exactly this behavior, right? So we can first start by talking about the ambitions of the flat space holography program. We should certainly give a nod to the millions of other researchers at this point that are studying this. Certainly acknowledge that this is in no means an exhaustive summary of all of those results, but we can certainly get back to that. So do you want to share your screen, Nikhil?
Yeah, sure. You can see everything fine? Okay. All right, so where would you like to start?
Yeah, so we can just start by talking about the modern understanding of how amplitudes involving gravity, QED, gauge theory factorize, which is sort of the starting point of your,
Okay, so I guess to start off with, we can ask ourselves, where do divergences come from for theories that involve massless particles? So for reasons that I think will become clear as we continue this discussion, I'll assume for simplicity at the moment, and it'll become clear why, that all the external particles are massless. That we're working purely with massless particles, and for people who are skeptical, you can just realize that for all intents and purposes, colliders deal with only massless particles. right? The particles are, if the electrons are usually moving at such high speeds that they're effectively massless, or if you're dealing with, say, the scattering of strongly interacting particles, then you're really dealing with the scattering of gluons or quarks, which are massless. So in the quark case, that's a slightly tricky question, but of course, most QCD scattering is, involves gluons, and those are massless for obvious reasons. So where do these divergences come from? Well, the divergences come from two places. So suppose you have say, suppose for the time being you have two momenta for the two particles, and divergences tend to come from several kinds of polynomials in the momentum. P and Q themselves are massless, so you have P square, you have Q square, but you can also have combinations like, say, P plus Q square, of which derivative is, of course, P dot Q. So these are largely the collections of polynomials that can give the Lorentz invariant combinations of polynomials. Any combination of these will obviously be Lorentz invariant, and you can get divergences from any one of these, right? So the obvious cases are, of course, when you have the particles on ship. So if you have a P square or Q square anywhere, you have a divergence. Those don't tend to show up because only external particles are massless. Internal particles are usually not internal particles are usually not on shell. But P dot Q, as we've seen, occur fairly often. And so we can restrict our attention to simply that and ask ourselves, when does P dot Q become 0? So this can, of course, become 0 under two conditions. One is when Q is really small. So which is the case with soft particles. So when Q becomes very small, or alternatively the wavelength becomes very large, P dot Q naturally goes to 0. But of course, there is another, more subtle and actually more important way that it can become 0, which is when P is simply collinear to Q. I'm sorry. What I mean by that is that P and Q are along the same direction. And of course, when they're along the same direction, then this simply implies that Q is, some constant factor times P, which literally just means that Q and P are not different, other than the fact that they have some constant ratio. And of course, we know for a fact that P square and Q square are both 0, which means that Q dot P is just P square or some constant times Q square. And that, of course, vanishes. This latter class of divergences are called collinear divergences, again, for obvious reasons. It happens when the momenta are literally in momentum space collinear to each other. And so we have to tell these apart. Starting out, we don't know. Starting off, the only information we have for any scattering process is how many of the external particles are collinear to each other, how many of the external particles are soft, and the fact that since we have quantum field theory in which the particles themselves are massless, we must have internal divergences which come from either these collinear or from these virtual pieces. And the formal statement of this is what we call factorization theorems. So what a factorization theorem tells us is very simple. It tells us that if we have a scattering process, the kinds of ones that we actually see in colliders, then we have to discriminate our amplitude on the basis of where we have collinear divergences, where we have infrared ones, and where we have the so-called hard amplitudes. The part of the scattering amplitude that does not have any IR or collinear divergence. For reasons we can get into, but I won't elaborate, the UV divergences aren't really important. They're all contained inside the hard piece. In the collider case, this is important because it's these collinear pieces that you really observe. If you think about these pictures that you see about the LHC, you have particles that are smashing into each other and then they come out. And then you see these long, collimated beams next to each other. And these are the so-called jets. And these jets are usually circumscribed by some angle. And all the particles are concentrated inside those angles. And for all intents and purposes, it's as though they're collinear to each other because the angles are so small. So you have a bunch of these jets which correspond to different collinear sectors. And you have various soft emissions which you can't see on a screen, but of course they exist. So this means that if you have any scattering amplitude, let's call it A. Oops. And suppose we're dealing with QED, so we'll call that QED. I drop the QED subscript from now, but of course we're assuming that we're working with QED. We have where the Cn denotes various collinear sectors. It's of course not exact. The Cn itself is a product of different collinear sectors. So these are the soft divergences that are coming from the virtual pieces. And of course, you have the soft divergences are coming from the real pieces. And just for sake of completion, you have the hard piece. Okay, so this formula looks like a mouthful, but it really isn't, because the Cn can be computed. There are techniques to do so. The soft pieces, we just saw how to compute them. At leading order, they're actually pretty easy to calculate. And the only reason we're splitting the virtual and the real pieces is we want to calculate them separately. They have different physical meanings. We don't want to conflate things that really aren't the same. And now the hard piece is usually fairly tricky. It's not easy to compute them. You have to define them in terms of renormalized Wilson coefficients. But recent work, not too recent, 2019, 2020, showed that we can probably compute these precisely, or at least we can define them precisely in terms of taking a bare scattering amplitude defined by, say, A, and in some clever sense, quotienting out these real and these soft and collinear pieces. So the hard piece actually admits of a real definition. It's not just that part which is not soft or that part which is not collinear. You actually can define these things exactly. So this is the form of any scattering amplitude. Now the question is, are there intrinsic definitions of the collinear and the soft pieces? The collinear case is tricky, so I won't get into it. But the soft piece, as it turns out, does admit of an intrinsic definition. And that was really what I was trying to do in this paper. So would you like to say anything?
Yeah, well, no, this is great. So, I mean, this is a little bit more of a sort of elaboration of what we saw by just trying to take this exercise seriously. We saw that there's going to be these virtual and real soft contributions. Now, of course, what we didn't think about were the collinear ones, right? Which would obviously also arise. And they're, you could say that, well, there's no sense in which you're going to see Q squared appearing in the denominator, right? I mean, unless you have P in P dot Q being proportional to Q, right? So it's kind of like an obvious sense in which it appears. So that's, it's a very good summary. And now what we're going to do is, I guess, give a different representation for the soft parts, right? So we're just going to focus on those. And another thing to comment on is that despite all the similarities we saw between QED and gravity when it came to the actual form of these soft factors, the factorization story is different. They probably want to comment on that.
Oh, for gravity.
Yeah.
Right. So starting with the gravity case, you would imagine that gravity is more complicated than QED. You would imagine that all of these divergences show up in gravity as well. Well, as it turns out, you can prove this, and it is not easy to prove. You can see it at the level of one. Weinberg has a short piece in his paper dealing with this, but giving a rigorous proof that this is true is not easy. It has been done, and I believe Bryce DeWitt was one of the earliest people who gave what you could credibly call a good proof of this. The idea, the result is that gravity does not have collinear pieces. So I don't want to use the same symbol. So I will just call this G. One of the banes of writing any paper is running out of symbols. So. And I put the times here. All right.
So is there any intuition as to why there are no collinear divergences?
So in the intuition as to why is the polynomial behavior, is the more, let's say, is the softer polynomial behavior of gravitational amplitudes. So if you remember the form of the soft factor, which you can imagine is the same, the divergence looks identical even for collinear divergences. You remember that you had a p square in the numerator, while you had only a p for where there was only one p in the case of QED. Well, it turns out that p square has the effect of dampening the collinear piece. So when you check your collinear amplitude and you use the factorized form of the amplitude, and you make sure you take into account all of the you take into account all of the right polynomial features of it, then the nature of the factorized amplitude in gravity ensures that the collinear piece is washed out.
I see. No, that's fascinating. Is there some physical story to tell about this? I mean, so you had a picture in the case where you had these LHC amplitudes where you see jets and so on. Does that mean that when we look at gravitational scattering amplitudes, whatever they exactly mean, in the regime where they are meaningful, you don't quite see jets? This is something else.
Right. It's I think the physical insight one should draw from this, to the extent that you can actually get physical insights from gravitational scattering amplitudes, and it isn't obvious that we can, but to the extent that you can, we should perhaps say that there isn't much knowledge to be gained from trying to understand gravitational particles actually scattering off of each other, but rather as carrying away, carrying a physical information like momenta through radiation. So as we'll see, the real way of looking at these soft divergences is as long distance radiation, where the information about the scattering amplitude is somehow stored by the long wavelength soft gravitons. And the insight that comes from factorization in gravity, I think, is that that's where all the key information lies. At long range, the long range radiative behavior of gravity, as opposed to highly energetic collimated jets that carry away momentum and energy, as you see in the case of the LHC.
Thanks. Okay, cool. So then let's dive into what you did in this paper. But okay, maybe we should preface it with some sort of celestial background. I mean, we can go one of two ways. We either proceed with your presentation of this of these results, and then we sort of infer in hindsight whatever it is we want to infer, or maybe we should say a word or two about a more general hope, sort of more general fantasy, and then, so yeah.
All right.
How would you like to do it?
So perhaps it's worth going over some of the rudiments of the technical details involved.
Yeah.
Like,
okay.
How we calculate things and what we would like to see from these calculations. Because, and I'm speaking only for myself, a lot of the physical insights from this were very post hoc. They came from using some of the simplifications that come with. They came from observing some of the simplifications that accompany the use of massless particles. And just observing these simplifications and realizing that they represent some information about boundary theories that were not obvious at first blush.
Well, good, then let's stick to this.
And since any talk about motivation post hoc would necessarily be achronological, it might be better for anyone watching to realize that much of the insight into this was actually very backwards. For me, I can't speak for anyone else.
Great. Yeah, let's proceed then.
Okay, so since we're dealing with massless particles, let's try to figure out a better way of parameterizing momenta when we're dealing with massless particles. So any massless momentum P is zero. That's how you define massless particles. So is there a way of parameterizing P1 through P4 or P0 through P3, depending on which side of that you fall, which makes it easier to, say, do calculations for one thing, but also to see what's going on in another? Is there a way of, say, understanding collinear divergences as 2 points approaching one another? Is there a way of looking at IR divergences as some constant going to zero, rather than as the momentum itself having long wavelength? Now, it turns out that the cleanest way of doing this is to use what is called the stereographic representation of momentum, which simply makes use of the fact that any momentum that is zero has only 2 degrees of freedom. There's more than one way of seeing this, but the simplest is always in hindsight. So let's just write out the momentum in this way, and we'll see that this is actually the best way of writing them.
Sounds good.
Okay, so this looks like a mouthful, but there are just 2 variables, z and the conjugate of z. Now, the conjugate is formal. For complex momenta, the 2 variables are independent. They don't necessarily have to be complex conjugates of one another, but they do have to be complex conjugates of one another for real momentum.
Right, yeah.
So, okay, yeah. Okay. So why is this a good way of parameterizing them? Well, it's a good way of parameterizing them because you can see, first of all, that P square really is zero. If you write it this way, it's a simple calculation. There's no trick involved. And the idea is that this parameterization actually trivializes a lot of the features of scattering amplitudes for massless particles. Now, of course, I've missed something, which is the energy of the particle. So in this limit, I can start off by just saying that the IR limit is just the one in which E goes to zero.
Right.
That's all the IR limit is. So the IR limit does not talk about any of the Zs. The IR limit only talks about the overall energy up front. So it really is when the particle is going to zero. And I guess more crucially, it's not Lorentz invariant fact, the IR limit. The IR limit really depends on the frames that you're working with. And you have to specify the moment of the other particles for the IR limit to make any sense.
Right.
Okay.
But I mean, the rough idea is still that it's like a scaling
It's
thing.
like a scaling.
It's like a conformal.
Ultimately
it's
it's
meant
like a
to be
conformal.
a
Yes.
specification of a Weil factor. Yeah. Cool.
Right. Exactly. Okay. So if now instead of P, since we want to work with more than one P, one particle is boring, we mentally make a note of the fact that for every P, we use Pi instead. So we denote the particles by Pi. The i's can run from 1 through n, any number, and correspondingly, everyone should regard the z's as zi's when we're discussing. So without belaboring that point, because we don't want to redefine a Pi each time. So let's compute certain basic quantities. P square, Pi square, as we've already pointed out, is 0. Oops. But what happens when we dot Pi with Pj? Well, it turns out that up to an overall factor, depending on how you define it, you have
That's very nice. Yeah.
where, of course, by the bars out front, we just mean that it's the complex conjugate. We just mean that it's the squared modulus of the difference between Zi and Zj. Now, what this means is that the collinear divergence really takes place when, if you view these Zi's as being punctures on a Riemann sphere, because you also want to talk about, moment at infinity. We know that the complex plane doesn't cover all the points that you can access. You also have a point at infinity, and so you have to have a chart that takes care of that. But of course, if you work with the Riemann sphere, then you can sensibly talk about all points on all complex points, and the Zi's can then be viewed as just punctures on a Riemann sphere. So now
Yes.
you already have some of the indications of what we mean when we talk about holography, because we have gone from four-dimensional particles, particles that live intrinsically in 4 dimensions. We weren't even thinking about 2 dimension when we define these particles. Now we have just a notational difference that renders these particles in some precise sense 2-dimensional. Because with the exception of the fact that they each have separate energies, which, like you said, are really scaling factors, each of the particles actually lives on the Riemann sphere, because they can be thought of as punctures on the sphere. And like punctures, they can move around. And when they come close to each other or they loop around each other, then they start to pick up phase factors and singularities that come from this difference.
Right. I mean, we do have word for this intuition, which is a stereographic projection.
Stereographic projection, exactly.
And this is like one of Penrose's favorite ideas, and it was sort of at the genesis of his idea of twisted theory. And I think that right now we're still using some very modest aspect of that. But I mean, it might be helpful to like pull up a little picture that I sent you over there of the exact projection. Yeah, so I mean, ultimately, what we're trying to say here is that.
Can you see the picture?
Not yet.
Oh, not yet. Okay.
But yeah, ultimately, what we want to move from is a picture of 4 momenta that are all null to a picture of exactly the celestial sphere.
You can see the picture?
Yes, here we go. Very nice. So the basic underlying idea is where the arrows go between the 2 points on the right-hand side ball and the 2 rays that lie on the light cone that is being depicted here. Right. So this is basically the identification that we have. And basically, when these 2 lines lie on top of each other, we have a collinear
linear divergence
singularity, and that's when those 2 points.
That's when those 2 points on the sphere actually fall on each other. Yes. This is sort of the interesting sense in which you can say that everything you've ever seen is a Riemann sphere.
Yeah, I mean, it
right?
really gives meaning to one's own perspective. That's why it's called the celestial sphere, right? Which is to say that if you were thinking about, I mean, one of like the old way of thinking about projective geometry was to just think about somebody looking down a train track
A
or
train
something,
track, and
trying to
the tracks meet at infinity. Yes.
exactly. So it's literally your perspective. I mean, if you take the observer O and then look at the past light cone, well, the boundary of the past light cone defines the boundary of their perspective, right? And
Right.
now the
Yes.
point is that on the one hand, insofar as anything that isn't a light ray is concerned, you would think that, okay, there's a lot of information there, but then what do light rays do? Well, they skirt the edge of the light cone. I mean, that's basically why it's called a light cone, right? And so that actually translates into the things you see, right? I mean, it's like you're surrounded by a sphere of light coming from various different points, and that is your celestial sphere.
That is your celestial
light
sphere.
rays
Yes.
have the nice feature that they are very insensitive to, let's say, certain kinds of scale issues. Right? The fact that the light cone is infinitely large doesn't change the fact that your perspective is ultimately this sphere.
Yes.
And the sphere could be as large or as little as you want it to be. The only thing that distinguishes them is their respective wavelengths, and that, that's what is encoded in the overall scaling factors here.
Yes.
But,
and it is worthwhile to note that it's only when these wavelengths are infinite that you record these as coming from infinity. Which is where they ultimately live.
Right.
Or perhaps that's not entirely correct, because you do record long distance. You do record particles that do not have infinite momentum, but or do not have zero momentum. But in terms of in terms of actually detecting these theoretically, one might guess even before actually doing the computation, that the part of any amplitude that actually captures the information at infinity is that which is tracked by particles that themselves have very long range behavior, which are precisely the infrared particles that we want to discuss.
Right. So that I think is a very good point as well. So one other thing to mention here is that all this talk of infinity takes us to the ulterior motive, which is to have some perspective of holography in flat spaces. So in asymptotically flat spaces, if you wanted to describe some dual gravitational theory, then you see this is a natural candidate for where to put it. But we'll make this sense more precise in what follows. So let's not try to give that away yet.
All right. So now we can actually start talking about these soft pieces of the amplitude in terms of this two-dimensional data rather than the four-dimensional data. So we won't look as cool as Weinberg does by having complicated formulas, but we'll understand something cute. So I suppose it's worth it. Okay, so we can recall that sticking to the virtual piece for now, we'll eventually get to the real piece. We saw that the virtual piece was the exponential of some function of momentum. So we really want to deal with the log of the of the virtual piece. So we'll do that. So we have So this looks like a lot, but I'll explain term by term. So the first part of this, the minus 1 by 8 pi square epsilon, is I've secretly skipped a feature, which is the renormalization energy, the mu and the epsilon and all that. But you can just think of this as using dim reg instead of polyvelars, which is what Weinberg uses. But the key part is this kinematical piece, which this matches exactly what Weinberg had. But the log zi minus z square is really the zero mass limit of Weinberg's formula. So Weinberg had this complicated function of momenta, and if you actually just take m goes to 0, there you get this.
Great. So let's, I mean, just to recap, recall that this was like the logarithm of 1 minus beta nm divided by 1 plus beta nm.
Yes.
Maybe it was the other way around. And beta nm was the relative velocity factor, which involved the masses explicitly. And you're saying, well, take the masses to 0. So, I mean, we could even look at that explicitly to sort of, let's say, contrast. So let's go back to our A factor. So this has a lot of the schematic features of what you're describing. The logarithm has been absorbed into your epsilon factor. This is the factor that we were talking about within the logarithm. And here we see that there's this, these two pieces under the square root. And what Nikhil is saying is, well, take beta to 0, or sorry, take m to 0.
Yes.
And then basically be careful about how you do that, and you'll discover that you have this simple looking expression to the z.
Well, see, if you take m to 0, then you can just expand the square root.
Yes.
And that simplifies all of it.
Right.
Because the denominator factor gives you the pn and pm, and the numerator factor ends up being, if I'm not mistaken, just 1.
Right.
So you have a bunch of these factors of half canceling out. There's a part that is very large, which so up to constant feature, so up to constants, you get the exact same result.
Nice. Good. Okay.
So you can already see some of the hints of some kind of holographic representation here, because you have the log of this virtual piece that's really only dependent on the log of the difference between the points on the celestial sphere. But most people who have taken any rudimentary course on complex analysis will immediately see the simplification that comes with this, because you have the logarithm of the difference, and that we know for a fact is just the Green's function of the Laplacian on the complex plane. Now we can test this by having hope I got the factors right. So I guess I would go so far as to say that so this and one more such equation were the only real insights in the paper, because once you have this, you can tell that this quantity should really be, at least should be computable in principle at least, but as it turns out, even in practice, by a conformal field theory that we're all quite comfortable with, which is just the conformal field theory of a free scalar. So we can start off with that. So if you have then we know that the OPE of up to, of course, overall constant factors, which means that what we're really dealing with is just the Coulomb gas. Because
Right.
this is exactly what the Coulomb gas is, right? You have a free scalar on the Riemann sphere, and you can insert instances of the particle of the Riemann sphere and the various ways that they correlate with one another, which is a simple correlation function to compute, should give you something that really resembles this.
Yeah.
And we know from what we understand about CFT exactly how to do this, because we can construct which I'll denote suggestively by and of course we have which is exactly what we want.
Very nice. Very nice. So basically, you're saying that you can just notice that this logarithm here is just a Green's function in 2 dimensions of free scalar. And the fact that you're actually trying to compute the exponential of this object means that you want this whole thing to appear in the exponent, right? Which then tells you that you want to look at exponentiated free-field operators, also known as vertex operators, and their correlation function, or even the leading term of their OPE, reproduces this factor.
Reproduces this factor, yes. What this, of course, means is you can take a bunch of these W factors, you can put them together, so you can take W1 through Wn, and you can compute the endpoint correlator of this. And the endpoint correlator turns out to just be this factor. Of course, you don't have the 1 by 8 pi epsilon, which you can fix by simply rescaling S. And of course, I'm not using the word rescaling lightly. It really is just a rescaling. So I won't go through all the details. I can if you're interested. But it follows exactly the same procedure as you have here. Instead of having 2, you have n, and the endpoint correlation function is just the exponential of this. And this particular calculation, though not for exactly the same problem, is there in, I believe, every CFT textbook that one reads, because this is just the Coulomb gas problem. And you see this come up everywhere the Coulomb gas exists. Like you see this in the BKT transition. You see this in the CFT literature about the Coulomb gas. You see this all over the place. And just for the more old-fashioned people around, this is exactly the same thing that happens in the fundamental string, where the fundamental string can simply be rewritten in this form, and you have this. The Polyakov action gives you exactly this quantity for the scattering of electrons.
Right, and just to mention, what's nice is this is a CFT, which reflects the fact that there's some scale and sensitivity of the kinds of objects we're looking at, even in the bulk, right? So basically, the idea is whoever can make it out to infinity is something that isn't sort of unaffected by issues of scale. That's why its behavior can be replicated by CFT in much the same way as we have in ADS-CFT. Sort of that's the more I suppose, like thorough packaging of this fact, but it's nice to see signatures of it here. And we can maybe sharpen this intuition more and more as we proceed. And as I understand it, you also have a story like this for gravity, right? So could you tell us a little bit about
Yeah.
what the
Now, since we've done all the hard work for QED already, most of this is the hard work. Realizing that this is possible, then the calculations are easy once you have this on hand. The case of gravity comes from just finding the analog of this equation and finding the analog of this. Because once you have those, just boils down to reconstructing the action, which you can do once you have all of this. So in the case of gravity, we can start that off by simply noting that I'm using kappa I and kappa j to denote the various ways the particles couple to gravity, because we want to keep this as general as possible. Assume at the outset that particles couple to gravity in different ways, and later we'll explain how we make contact with Weinberg by keeping track of this. So they have the exact same form. Uh, there's almost no difference, except for the fact that you have the Zi minus Zj out front.
Very good. And this again goes back to what we noticed
Right.
in the Weinberg papers, where we had those beta factors sitting outside the log.
Sitting outside the log. Yes, exactly. And of course, more astute ones might notice this. I didn't when I first saw this, that this is actually a source of the collinear divergence not coming up in gravity. Because, you take the Zi, go to Zj, this quantity actually goes to 0.
Very nice. I mean, that is that is a somewhat astute observation.
It should be obvious, but it wasn't to me when I first saw this. Go to a new. So the question we have to ask is this the correlation function of some theory? I mean, or is this computed by the correlation functions that are furnished by some simple theory? So we do the exact same experiment, which to me was an experiment when I first did it. So that's why I'm going chronologically. I just try to I tried to apply as many operators on this as I could and check what the result was. It turns out the result is widely available if you know the literature. It's available in the famous paper on the BKT transition. I didn't know any of this beforehand, so it boiled down to much more brute force work. You look at this function. So it takes some work to go over, but you have 1 by I think this is right. Let me check. Yeah. You can fact check me at any point. Which means that once you apply, this last part is not so hard to check. If you apply the Dolbeault operator twice on this, you have, I'll just paste this. which is the key point that I'd like anyone to take out from this. This kinematic factor out front in Weinberg's soft factor is just the Green's function of the square of the Laplacian, or the biharmonic operator, as some people call it, which means that all you have to do is take the correct analog of this theory, where the kinetic operator is not the Laplacian, but the square of the Laplacian, and you're in business. So you have there are good reasons for writing it in this form. I can get to those. One might think that you can write it as, for example, the square of del phi times the square of the conjugate of del times phi. But that turns out to be not Lorentz invariant of the two sphere. It turns out spurious symmetries, which we know for a case are not valid here. So this is the right form of the action that you want to use.
So you're saying that trying to take the square of that operator isn't just related to this by some integration by parts?
Is not no. Yes, that's exactly what I'm saying.
Good.
Where the operator that you're this will come to a point which I thought was cute. The operator that you're squaring, in a sense, to get gravity is the Laplacian, not the individual partial differential operators.
Good. Okay.
But it's the Laplacian that you have to square. So that's
it's not
the key point.
del bar squared, del squared. It's del bar squared.
Yes. And there is a difference in the theories that you get by doing this.
Okay, good.
All right. So the rest is, I guess I should use a different symbol. I can use just phi. And of course, and once you take the correlation function of n such operators, you get precisely Weinberg's virtual soft factor.
That's very cool. That's very cool. So you just have a different kinetic term, but then you still go form the same kinds of vertex operators, and then you just compute TOD and you get the same factors. Nice. And going back to the title of the paper, you probably want to comment on the double copy-like relation between these two, theories.
So for would you like me to give some basic background on what double copy is?
Sure.
The double copy is a conjectured relation between gauge theories and gravity, where observables in gravity are obtained by either literally squaring or by effectively squaring via some kind of complex operation the corresponding observables in gauge theory. With the selling point being, with the alleged selling point being that these things are always easier to compute in gauge theory, and there's always a clever prescription, and the claim being that there's always a clever prescription to translate these into quantities in gravity. Now, as it turns out, the double copy is extremely hard to do for serious scattering amplitudes. So suppose you have a three loop 7-particle amplitude in n is equal to 4 supersymmetric Yang-Mills, and you want to obtain the 3 loop 7-particle scattering amplitude in n is equal to 8 Yang-Mills, in n is equal to 8 supergravity, which is the claimed double copy cousin of n is equal to 4, it is not easy to do. In the case of 3 loops, it isn't obvious the relation exists. We do have some analog of a double copy relation up to 2 loops, but at 3 loops, we get confused. But one of the cute things I saw in this paper is that there really is a very precise double copy, which, regardless of whether or not you find it interesting, does exist. It's just everything in gravity is obtained from QED by simply making the following 2 substitutions. So you have I'll suppress the eters. We'll absorb them into the definitions of E.
Right, so you probably want to square the thing on the right, the top line.
Yeah, sorry.
Yeah.
That's it. So it's almost literally just a color to kinematics translation. So
right.
you take the kinetic operator and you square it. Then you take the color, which in this case is E, the charge, and you just convert it to kinematics, the kappa, which is the coupling to gravity, which we know from high school is kinematics. And we later see even in this formalism that it really is kinematics. The kappa is the gravitational coupling.
So at the risk of jumping ahead a little bit, so this is what you're showing between QED and gravity. Yes. Now, there's a version of this entire story that's been worked out for non-abelian gauge theories, if I understand correctly. So yes. Is there a relation of this kind there where you actually strip out color factors and you just keep the kinematics? Oh, very good. Okay.
So there's an analog of, so I don't know if we'll get to this, but there's an analog of the soft factor for QCD. You have to define it in terms of what's called the cusp anomalous dimension. Because factorization in QCD is a little trickier than it is in QED. But you have the almost the exact analog of the virtual soft factor in QCD, and they depend on the color, on the adjoint color matrices instead of the EIs. And the relation between that and gravity is replacing the color piece with the kappas.
Very nice. Now, there's another physical question that I had, because I think that this is, we could linger here until the very end, and I think that that'll be worth it. But there's a clear difference I see between the role of E and kappa, which is just the signs for E that kappa can never achieve. Right? Yes. The fact that there's only, so in some sense, you can envision a Coulomb gas. So, I mean, you literally have a Coulomb gas in the QED case. In the gravity case, you have some modification in the kinetic term, but you also have modification in the sense that you can never accomplish screening in this story, right? So there's never a sense in which you can be beneath a threshold where the putative vortex-like configurations are confined because they have no anti-vortex-like object to which they can
bind themselves. Yes,
they're forever liberated. And I'm very curious. So this Lagrangian level substitution can probably only dynamically occur in the deconfined phase of the Coulomb gas.
Right.
Where you have liberated vortices and
liberated vortices. Yes.
Right. And I think that that's very fascinating. So do you have some understanding of what the winding number operator is in this story?
In the gravity story.
In both stories. So you have these dual models, right. Two-dimensional models, and then you can very clearly define a winding number operator, right? Just a simple integral formula. Do you have a sense for what the relation is, or sort of what the meaning is? It's probably just something, yeah.
So if I understand you right, I suppose you can define the winding number by taking the current that's caused by the insertions of these vortices, and then asking what happens when you wind around the singularities of the current, and what number you pick up by doing this.
Yeah, well, basically, if you thought of phi as a form, well, I mean, if you thought of d phi as a form, then the winding number is just the integration of this form over one cycle.
Right? Over
so
one, right?
Basically, what it is, yeah.
Right. So yeah, exactly. So if you have a current piece in the action that has the form of J phi, then here J would just take a sum over delta functions. And the winding operator here would just be winding around these delta functions and would pick up the factors of these EIs.
Good. So
right?
You're literally identifying. So the total winding of the configuration is the charge, the total charge. Is that right?
Yes.
And by gauge invariance, that's always going to be 0. Is that right?
So in this case, not by gauge invariance, but by the invariances of the Coulomb gas model itself.
Right. So sorry. So you mean okay, let's go through this in a little bit more detail and correct my statement by saying that I mean the signed sum of charges.
Yes. Yeah.
Okay.
See, if we absorb the eta i's into the charge,
yeah,
then you're fine. Because
right.
if you have a positive and negative charge, and at the level of quantum field theory, they're incoming and out. At the level of quantum field theory, these can either be incoming and outgoing, or they can be both incoming.
Right.
These differences are trivialized in the Coulomb gas level.
Cool. So what is the symmetry here that is being preserved to ensure that this sum is always good?
So you can tell that where by that's it. So what I mean by this is that phi is just changed by a constant. So we have a shift symmetry where we shift phi by some constant number, and S is obviously invariant under this, because you can just look at the form of the action. You have derivatives acting on phi, and derivatives acting on any constant give you 0. The reason it's obvious is because you can shift either of phi, and it really doesn't matter, because what you get is a boundary term. You get a term that's proportional to the derivative of phi, and so long as you have 0 contributions on the boundary, you can always declare that to be 0. In the case of gravity, you have an analogous analogous symmetry, but in this case, it is that's the symmetry in the gravitational case. It's easy to check.
Right.
And
because you have more than one derivative in the kinetic.
You have more than one derivative in the kinetic term.
More than two.
Yes. So all the transformations that either cause S to trivially vanish, versus those that are left with boundary terms can be chalked down to just this 4 parameter group of transformations.
Right.
This should already be suggestive, but I can go into that. Great.
But what's happening here is that the bulk manifestation of the gauge invariance, and it's going to become a symmetry in this
in the two-dimensional model. Yes.
Great. Just as we expect to see in some holographic
holographic theory. Yes.
Holographic theory. Now, of course, it's very subtle as to exactly how this is happening, because the field source or field identification between bulk and boundary isn't something that's been entirely pinned down here. Now, maybe we can attempt to do that with however much time we have remaining. There is a lot of work that this connects to, but I don't know if we'll have time to get through all of it today, because we've already been discussing for quite a while. But this does hit at the heart of your ideas, right? So you have a follow-up paper to this where you consider the problem of having multiple real soft emissions.
Real emissions, yes.
Right. And so maybe you could briefly comment on the modification that you needed to entertain in order to accommodate that.
Right. So without going into too many details, I will just say that you can deal with one real emission using this model. But when you have multiple real emissions, you have the issue of, say, two different phi insertions touching each other. So I wanted a way to define real emissions in terms of current insertions into the correlation function. So I wanted to define an operator, say we'll call it J, let's say J of Z times now the reason why, just a sec, and I'll put, okay. So the reason why I wanted an equation that looks that looks like this is precisely the form that Weinberg's soft factor will take if we're working with massless particles. It's not hard to check. If you compute the if you compute the dot product of P and epsilon and take the ratio with P dot Q, you get precisely this quantity. Now, why I wanted a J of this form is because one way to think of W's is, of course, as abstract operators that give you the virtual piece when you compute the correlation function. But another way of thinking of them is actually as duals of the particles themselves and as insertions on the celestial sphere. So you're inserting particles on the sphere by really inserting these W Wilson lines, as one would like to call them. And the analogy with Wilson lines, of course, is that these are objects which in some clever way encode gauge invariance via this symmetry that we've already seen on the celestial sphere. Right. The correlation function contains information about the infrared soft limits, but these insertions, but the W insertions themselves actually only depend on the momenta of the external hard particles.
Right.
They don't carry any information about soft particles themselves. So now soft particles, real soft particles have to be introduced via some other current operator that once come into contact, once it comes into contact with any of the W's, resolves into exactly the soft piece that you're looking for the.
Okay.
And there's a natural candidate for this, which is just the current that comes from the void identity corresponding to this symmetry, right? Because that's where, if we want to sort of have this all in a nice physical picture, then we would imagine that just the same way as charge conservation was equivalent to this symmetry, the shift symmetry on the celestial sphere, then the soft theorem, which itself has as a derivative of it charge conservation, should be in some sense related to the Ward currents of the theory. And so I wanted to define the J in terms of a Ward current. But so you can always define J as, for example, this is the Ward current. It can be checked. It's invariant under the shift symmetry. If you want the anti-holomorphic piece, you can take that, and that gives you the negative soft emission for negative helicities. But anyone who's computed OPS can immediately see the problem with this, because if you have two such insertions corresponding to two soft particles at, say, Z and Z prime, then you have the J's themselves hitting each other. And that gives you a 1 over Z square, which is a highly collinear divergence, which only shows up at subleading order. And we don't want that. So what I did instead was just refine this theory. I can go into the details, but it's just technical. It's purely technical. I have two phis instead of one. And I maintain a metric in the space of these phis, a two-dimensional metric, that interpolates between the phi that I would like to keep in the W's, which hit each other and give me this log, as well as another phi, which does not have an OP with itself. So I can define the J's in terms of that phi, but it does have an OP with a W. So that gave me an upper triangular matrix for the for the metric in phi space. And that theory, it turns out, contains both information about contains the information about both the virtual and the real solved divergences.
Very nice. So you're saying that you went from this relatively simple free theory to a sigma model with some constant metric, yes, but it had some, you basically modified some of the word identities.
And
okay,
so
very nice. So
you see in this picture, the word identities corresponding to these word currents coming from, in the case of QED, the shift symmetry, and in the case of gravity, the generalized shift symmetry, correspond exactly to charge conservation in QED and to Weinberg's version of the equivalence principle, stating that all these kappas have to be equal to each other in the case of gravity. So four-dimensional statements about gauge invariance or the equivalence principle really reduce down to word identities of these two-dimensional models, which is what you want in a holographic theory, right? A 4D, 2D dictionary. And this furnishes that.
Nice, nice. So before we move on and conclude, you might want to comment a little bit on so we talked about how the Coulomb gas is related to the QED model.
Yes.
But there is a known model that also corresponds to what you have written here for the gravity dual. So could you comment a little bit about that? Because it's maybe a little bit exotic for the kind of people in our audience.
For the known model, you mean what this means?
Yeah,
this model means?
The disclination model, yes.
The disclination model, okay. So this is what's called it's what's called a biharmonic theory for obvious reasons, because the kinetic operator is biharmonic. And it turns out to define a specific class of topological excitations that show up in BKT-like transitions. And what the kinds of, so they undergo topological transitions that are analogous to the BKT transition, but they take place when you have different kinds of current operators. So you can have, say, a current operator that attaches to phi, where the divergence in the delta function is more divergent than you have in the Coulomb gas version. So when the delta function itself carries, say, a derivative operator in it, so you have the current defined in terms of delta prime rather than delta, then the disclination model gives you a correlation function that matches the Coulomb gas case. And then you can talk about its BKT transitions and so on. Now, if you were to ask where this model actually comes up physically, it comes up, I believe, in models of elasticity in lattices. So if you have lattices placed, lattice points placed in particular ways, and you have excitations in this lattice, then the ways that the sort of elastic restoring force relates them turns out to be very similar to this biharmonic model.
Very
and so
nice.
I believe they have applications in soft matter, and you see this coming up all over the place. But yes, in our circles, this is extremely rare.
Now, the question I have is whether the BKT transitions in these models arise from there being some distinct signs in the charges. So, I mean, do you have defect and anti-defect type configurations that are confining at some temperature? Is that the story?
The problem I have with that is I don't really know what temperature means over here.
No, sure. But I mean, in the original models, is there?
In the original models, yes.
Okay. Because here, clearly, you're stuck in one phase.
You're stuck in one phase, yeah.
And that, I think, is an important, or maybe an interesting thing to think about, the fact that you are now dealing in some sense with half of a Coulomb gas.
With half of a Coulomb gas, yes.
And you're compelled. This isn't just a consequence of the symmetry that was probably present even in those models, right? I mean, even in those models, you have the same currents, right? Yes. But I suppose the important fact here is that from the get-go, the kappa I are not negative.
Are not negative.
They can't be negative. And that is very fascinating from the perspective of the statistical physics of these things, because I cannot imagine that these would be, at a certain temperature, they're certainly not going to be stable. I mean, I don't even know exactly what that means, right? And Whether that has some manifestation here is another question,
Yes.
because you don't have a notion of temperature necessarily. And to cook one up, you might have to entertain something very bizarre. And this is just a question. So now let's move towards speculation, because we don't have time to go over related works. But the only way in which you can talk about some kind of thermal partition function or anything of the sort in this celestial story is when you change signature to, let's say, for bulk dimensions, you go to having two time-like directions. Now, of course, another way is to go completely to Euclidean space, but the more fanciful one that people have been talking about recently is to go to this kind of client space where you have 2-2 signature. Then the natural topology of the asymptotic boundary becomes a torus. Well, it's torus fibered over a line in much the same way as here you actually have these spheres fibered over a line. But okay, I mean the intrinsic space-like geometry is a torus. Well, it's not really a space-like torus. It's a different kind of torus, but still, there's some way of maybe imagining the partition function there. Do you see any hope of just going through the motions here, right? And then just taking for granted that the model goes along for the ride. So set aside specific details. So the model goes along for the ride. Will we be computing the thermal partition function of this theory in that context?
If we're working with, if the answer is that the only change made is to the Green's function, then perhaps that's true. Perhaps we're really computing the thermal partition function. But the translation between any parameters we have here and whatever temperature means, I think would involve some work, even if it's only intellectual.
Sure. I see. Well, yeah, I mean, it's just that in that context, you might have some more of a sense of what's possible. But then again, we don't yet have a sense that this is an accounting of the spectrum of the dual theory in the same way that you would have that in regular ADS-CFT, because here you're capturing the soft factors and not necessarily the rest of the amplitude. So very briefly, if we can try and do a little exercise to maybe get a handle on what the GKP dictionary might look like.
Right.
So what we're saying is we're trying to match the S matrix. So let's call it S matrix with a more conventional correlation function, right? So we have a more conventional correlation function. So it's an S matrix with some arguments is going to a correlation function in the dual model with some arguments. Ideally, in entirety, this would be what we would want. Now, the S matrix itself has some factorization, right? So the S matrix has, I'll just use your notation, collinear times A. Soft with virtual particles times you have the same thing with real. Times the genuinely hard part, right? So this is, let's say that this is a sub n, where n is the number of particles in the story, right?
Now, you want to change one of those to real.
Yeah, you definitely want to change one of these to real. Great. And so you have an accounting of the middle two, which is good because maybe, and I don't know if someone's already done this, but we can backtrack. So this correlation function / S matrix level identification, typically in ADS-CFT, it would start from some more primitive identification between an evaluation of some object generating function on shell and some other object on the boundary. So on the right-hand side, there's always going to be, for lack of better word, effective action, dual, right? As a function of either sources or operators. So we'll leave that unspecified for the time being. Question is, what will we have on the left-hand side? From my perspective, the natural candidate for what we have on the left-hand side is an object that I've only seen discussed thoroughly in Nayer's quantum field theory book, which is the S matrix generating function. So
Right.
what notation? I think that his notation is to call it mathcal F. Now, what does the S matrix generating functional depend on? Well, the S matrix generating functional depends on some sources, which he calls verify. So, well, okay, let me just leave this unspecified, and let's try to work out what should happen here. Because this is an exercise I cannot think of anybody better to try and run through with. And if you already see a similarity, you should tell me. But
Yes.
I've never seen this done. But what's the basic mechanics of the statement that we have about S matrix elements given curly F? Well, the statement is that the S matrix element, which if you want to see as taking arguments in momenta, right? So that that's what it depends on, the n external momenta, is given by basically multiple, so you have multiple Fourier transforms. So you have I, where you have the product from 1 to n of mode functions, right? So this is the only difference with every other kind of generating function formula you would have seen, which is that you have mode functions.
Yes.
Xi times what we would always write down, right? So
some kind of
you
LSZ
have,
reduction.
Yeah, so the LSZ reduction has been worked into this. There's no LSZ. So from this perspective, there's no LSZ anymore. All you have is verify that depends, so you have
Right.
F that depends on some abstract sources verify. Let's not use verify because we've already committed to some meaning of phi verify. Let's call this calligraphic J, big J. And you have delta calligraphic J1, which is a source depending on space, right? So you have 1 all the way to n. So basically, you're doing essentially a kind of Fourier transform of an otherwise standard formula for generating these S matrix elements. Now, where does LSZ come in, which is a good question. LSZ comes in by saying that actually, what is mathcal F? Verify. Well, okay, let me just be careful about this. Okay, never mind. So mathcal F verify is nothing but, I think it's proportional to, this is where fact checking will be much appreciated. But we take Z, what we call the generating function, with its sources being set to solutions of the free field equations.
I see. Okay.
Of phi. Of mathcal J, we call mathcal J. So sorry, I wanted to commit. This is the rough format of what you're going to have. There might be an exponential factor, some Gaussian exponential factor that I'm missing in this proportionality.
Do you mean the inverse of?
Sorry, the log.
No, but do you mean the inverse of the operator?
So the inverse of this operator? No. I really want to then. So what I want to do is take derivatives of log Z with respect to J, and then set J to 0.
With respect to J or curly J?
With respect to regular J, and set regular J to 0 to compute correlation functions.
I see. No, because you've taken the deltas with respect to curly J's.
Here, but what I want to do here is use LSZ, right? Yeah. So what I want to do is say that all of these sources are solutions to free field equations.
Yeah, see, because when you have when you have a source that's coupled to a field, then the field the field is defined in terms of taking whatever operator you have and acting the inverse of that on the source. So here your sources, So here, if your
So
sources are curly
this isn't a
J's,
Legendre transform though. This isn't Legendre transform. That's the difference. What you're trying to
I see.
do is you're trying to impose. So what is Legendre transform? Is the relation between log z and effective action big gamma.
Yes.
So there you're going to see what you're describing. But here the idea is I compute correlation functions by taking derivative of log z with respect to j. But then on top of that, I want to set j to 0, which means that I want that I have the solutions to free field equations being the things that I differentiated with respect to. And then through chain rule, you'll discover that if you wanted to relate that to differentiating with respect to
I
j,
understand that. Right. You're going to have to multiply those by the inverses. I see. I get that.
Yeah. So it's kind of a very nice thing. And you see ultimately this f, right? It's basically the exponential of, so f has a nice formula in terms of the interaction action. So mathcal f of j, curly j, is the exponential of, let me write it in some simplified notation, otherwise it will get out of hand. Gal j, g, delta mathcal j. So basically what you're doing is taking this object. So f is almost the interaction action. That's actually just subtracted by all these propagator terms, which is how you have the whole LSC being baked into all of this. Also why its expansion in modes computes the S matrix elements, because you see that this is like the first thing you did when you started developing Feynman diagrams. Also, another nice thing. So this means the functional derivative with respect to j dotted with the argument of g dotted with another functional derivative with respect to j, right? That's what this abstract thing in the exponent means. F computes S matrix elements. S matrix elements are RG invariant, right? Let's say that we put a cutoff in G and then take the derivative of this with respect to the cutoff, set it to 0. You immediately derive Polchinski's equation.
I see.
Okay. So it's like a sort of repackaging of Polchinski's equation. Now, I think that we want to maybe have some version of this, right? So there's going to be some factorization of f, right? But this factorization of f really comes about through this, right? So you have all these Fourier transforms, and you essentially want to say that there's going to be some regime where, oh, okay, some of these are gravitons, some of these are photons, so they have some soft part, right? So you want to take this like a soft part of f, and then you have a relation between this soft part, which is factorized, and whatever the dual theory is, right? But
yeah. So you have basically a product of such formulas.
Exactly. So you have a product of such formulas. That's the meaning of factorization, right? So then the question becomes whether. So can we develop something like this? I suppose this is our homework exercise. If you can develop something like this, right? And then say, okay, you have a relation between matrix elements that just drops out of the sort of penultimate identification. You might have identified the soft part of this for QED. So it would be, I think that would be very satisfying to give this some sort of a holographic background at the end of the day. And also, I mean, the fact that this thing's RG invariance is just a Polchinski equation is, I think, very interesting, because then you can say, well, what is the implication of this having a factorized form, and also that there are these soft theorems? Can you have some self-consistent identity based on varying with respect to an IR scale, not just a UV scale? Right. So this is another thing that I've always wanted to understand.
So one unrelated comment, and it's actually a question. The biharmonic theory that I've written down is not a CFT, is it?
No, because the
2-point function is not.
Yeah. Well, but then again, is there, so okay, what we would normally call the primaries are not primaries.
Yes.
But is there some operator that we could think of as a primary? That I guess is the question.
So there is no one operator, I think, but there is, of course, I think, a pair of operators.
I see. So I mean, that's the thing, right? Like you could say the free theory by itself you can't really call it a CFT by just looking at the axioms, because you'd say if the fundamental field correlation function doesn't satisfy this isn't of the right form. Whereas if you look at the vertex operators and currents, you say, okay, with respect to these, you have an algebra realized.
Right.
Now, in the biharmonic theory, you have a similar story, right? You don't really have that the
Yes.
dual form is realized. Now, that doesn't change the fact that insofar as the soft factors are concerned, you are not dealing with the CFT, right? You're really not. Your correlation functions are something else.
So it's it's something that's always been bothering me, because at least for ordinary Einstein gravity, we might have to make peace with the fact that the entire theory perhaps is not dual to a CFT. So a gravity CFT dual might really not exist, because we know that at least the soft piece is not a CFT.
No, I think that's totally fine. I'm happy to accept that fact, because it's really a quirk of, like, when you have ADS asymptotics, it's a quirk of the fact that you have ADS asymptotics, that you can identify the action with that of a CFT. When you have this gravitational theory, the structure is just not that, right? When you have an asymptotically flat boundary, it's simply just not that, and it reflects whatever it is. I think the more important question is whether you can develop a dictionary like this,
right?
Which then has you see, once you have this for all sources, you will never lose, right? Like, no matter what you do, you always get the right result.
You always get the right result. Yeah.
So the point is, can we peel this from the effective action on shell? Now, by definition, you always can, and the reason for that is that if you went through with the Legendre transform formulae that we were discussing, then you will find that actually the following relation holds. You basically compute that object through the effective action on shell. So there's just no sense in which you ever lose, right? So the effective action with sources constrained to be on shell, or rather, with the background fields constrained to be on shell, computes for you the generating function of S matrix elements. So that's an unavoidable fact.
Yeah.
And now, of course, what you want to develop probably in a thorough holographic dictionary is to go beyond this, right? You want to be able to go beyond the fact where you have background fields that are strictly on shell or whatever, but nevertheless, this is still true, right? And you use this fact implicitly when you do all kinds of other calculations, right? So, for example, you compute Coleman-Weinberg effective potential and infer beta functions from the scaling properties of the Coleman-Weinberg effective potential. On the other hand, you do the regular Feynman diagram calculation to compute the renormalization of coupling constants, and you get the same beta functions by doing one or the other. And then the reason for that is that you just pick a particular term in the expansion of each of these two different things. On the left-hand side, it's the textbook Feynman diagram calculation.
Yeah.
The right-hand side is what you get from the Coleman-Weinberg effective potential. So anyway, this just goes to show that there's the thing I feel is a bit missing is the development of what the scale radius duality means in this story, right? And maybe, I mean, I don't know what the best test bed is. Like, gravity is nice, it's complicated, but in certain senses it's complicated. Maybe in gauge theory there's a slightly better handle. But on the other hand, everything else we know about the scale radius duality and ADS-CFT all comes from understanding the gravitational sector. I think that's where it's best identified.
Right.
So there are many options here.
Cool. Yeah.
Yeah. Well, I mean, anyway, this is I guess, jumping off point. It's a good place to stop.
Yes. Yeah.
But we've gone through a lot, but there's just so much more to go through. This is essentially a third of what we thought we would actually discuss.
Right.
Which goes to show how ambitious we were, but it also goes to show that we are necessarily a recurring guest.
Okay.
So thank you so much for your time, Nikhil.
Thanks a lot for having me on. This was very fun.
Yeah, great. So if you like this, please like, share, subscribe. If you disliked it, dislike. So this is Theoretically Podcasting, and we'll catch you next week.